Okay, so grades, some of you notice, some get notifications, others don't, but we posted grades today, second period, so some of you will notice you have a grade. Remember that grades will change the more you have to averaging with that grade. So your grades drop to a B already, just know the more worksheets that you do, then that average is going to change. Same thing with there's no tests in there right now. So when you take your first actual test, because I didn't count that placement test as a test, kind of as daily work, because it was more or less just for me to know who's in the right class, who maybe might need to do, okay? So the counselor's already been notified, so if you got spoken to by the counselor, then I made a recommendation. Okay. If you didn't, you're good. It's just in there as a grade, okay? I went 30% or lower on the placement test, which I believe was like 8, but you only got 8 right out of 27, so 8 and lower, had some zeros, so that's like a big red flag, you know, maybe might go into it, so. Anyway, so those are posted, so just keep that in mind. So when we have our first test, because remember we don't test on each little section, we'll do like this section, it will go 1 through 3, 4 and 5, and then 6 and 7, then we'll review 1 through 7, and then we'll test on 1 through 7, okay? So you'll have a test, and then it will be a while before we have another test. So until you have more tests in there to average your grade, then you may or may not look appetizing to you for a while. So just know that it'll change, okay? This first section, which most of the year is not going to be like this, there's not going to be a whole lot of vocab. We'll be doing problems together, and I'll give you sample problems, give you the steps to go through it, and then you'll try it. This is the first section. It's got a lot of vocab. So generally we will not take this many notes on vocab. But we've got to start memorizing what these terms mean, okay? So I will go through this. I'll give you some sample problems where they'll say, give an example of commutative property, or they'll give you an example of the problem and say what property is it. So it's just going to go back and forth. Okay, so for right now, it's vocab. So I'm just going to lower the light, make it a little bit better. Now that the cardboard's on my back window, it's super bright. Okay, so this first part is just examples of each one of those. So that when on your worksheet, so you're writing this, on your worksheet, if they give you an example of something, you're like, well, you know, what does it fit in? Is it a real number? Is it a rational or irrational number? Is it an example of an integer? So that you have samples of each type. Okay, so you can write that. Okay, those that are still writing, keep writing. I'm just going to talk about these. So counting, or most of the time you'll hear natural numbers. It's just when you start counting, I don't say 0. Okay, I say 1, 2. That's why they call it counting numbers, but 0 is not included. Okay, all whole numbers are basically non-negative numbers. Okay, so your whole numbers are going to be 1, 2, and it's not portions of something, so it's not going to be decimal. It's whole numbers. Okay, starts with 0, and then the rest of your counting numbers. Integers are all your whole numbers, positive and negative. Okay. Rational numbers. Now the difference between, and we're going to watch a real quick video, and I know Cons tends to stutter and repeat himself as he's writing. He repeats the word that he's writing, so bear with it, but it really does stick in your head because he gives some great examples. Okay, rational and irrational. Those tend to be the two that people get confused which one's which. What is rational? What is irrational? What does the word ratio mean? What's an example of a ratio? When what? To what? 2 to 1. Okay. So you can write it with the decimal in between or the word 2 in between. What's another way that you can compare it? What? Fraction. Okay, so he's going to talk about that with ratio, it's a number that you can represent as a fraction. Okay. Where irrational, you cannot represent it as a fraction. Okay, because pi goes on forever. Square root of 2 is not a perfect square, so if you were to put it in your calculator, it would go off your calculator. There's no terminating decimals. Okay, so that's ratio would mean you could represent it as a fraction, where irrational you cannot. Okay, and then real numbers basically. Okay. All right, so we're going to watch this real quick. So just pay attention to the examples that he's giving. Find it.
rational numbers.
You repeat the words.
Rational numbers. And the simple way to think about it is any number that can be represented as the ratio of two integers is a rational number. So, for example, any integer is a rational number. 1 can be represented as 1 over 1, or as negative 2 over negative 2, or as 10,000 over 10,000. In all of these cases, these are all different representations of the number 1, ratio of two integers. And I actually obviously can have an infinite number of representations of 1 in this way, the same number over the same number. The number negative 7 could be represented as negative 7 over 1, or 7 over negative 1, or negative 14 over positive 2, and I could go on and on and on and on. So negative 7 is definitely a rational number. It can be represented as the ratio of two integers. But what about things that are not integers? For example, let us imagine, let's imagine 3.75. How can we represent that as the ratio of two integers? Well, 3.75, you could rewrite that as 375 over 100, which is the same thing as 750 over 200. Or you could say 3.75 is the same thing as 3 3/4, so right here, 3 3/4, which is the same thing as, that's 15 over 4. 4 times 3 is 12, plus 3 is 15. So you could write this. This is the same thing as 15 over 4. Or we could write this as negative 30 over negative 8. I just multiplied the numerator and the denominator here by negative 2. But just to be clear, this is clearly rational. I'm giving you multiple examples of how this can be represented as the ratio of two integers. Now what about repeating decimals? Well, let's take maybe the most famous of the repeating decimals. Let's say you have 0.333, just keeps going on and on forever, which we can denote by putting that little bar on top of the 3. This is 0.3 repeating. And we've seen, and later we'll show that how you can convert any repeating decimal into a rational, as the ratio of two integers. This is clearly 1 over 3, or maybe you've seen things like 0.6 repeating, which is 2 over 3. And there's many, many, many other examples of this. And we'll see any repeating decimal, not just one digit repeating, as many, even if it has a million digits repeating, as long as the pattern starts to repeat itself over and over and over again, you can always represent that as the ratio of two integers. So I know what you're probably thinking. Hey Sal, you've just included a lot. You've included all of the integers. You've included all of non-repeating decimals. You've included all of finite non-repeating decimals, and you've also included repeating decimals. What is left? Are there any numbers that are not rational? And you're probably guessing that there are, otherwise people wouldn't have taken the trouble of trying to label these as rational. And it turns out, as you can imagine, that actually some of the most famous numbers in all of mathematics are not rational. And we call these numbers irrational. Irrational numbers. And I've listed just a few of the most noteworthy examples. Pi, the ratio of the circumference of the diameter of a circle, is an irrational number. It never terminates. It goes on and forever, and it never repeats. E, same thing, never terminates, never repeats. It comes out of continuously compounding interest. It comes out of complex analysis. E shows up all over the place. Square root of 2, irrational number. Phi, the golden ratio, irrational number. So these things that really just pop out of nature, many of these numbers are irrational. And you might say, okay, are these irrational? These are just kind of these special kind of numbers. But maybe most numbers are rational, and Sal's just picked out some special cases here. But the important thing to realize is they do seem exotic, and they are exotic in certain ways, but they aren't uncommon. It actually turns out that there is always an irrational number between any two rational numbers. And in that, well, we could go on and on. There's actually an infinite number, but there's at least one. And so that gives you an idea that if you can't really say that there are fewer irrational numbers than rational numbers. In a future video, we'll prove that you give me two rational numbers, rational 1, rational 2, rational 2, there's going to be at least one irrational number between those, which is a kind of a neat result because irrational numbers seem to be kind of exotic. Another weird thing, that I took square root of 2, but you take the square root of any non-perfect square, you're going to end up with an irrational number. You take the sum of an irrational and a rational number, and we'll see this later on. We'll prove it to ourselves. The sum of an irrational and irrational is going to be irrational. The product of an irrational and a rational is going to be irrational. So there's a lot of irrational numbers out there.
Okay, get the gist. Which one's rational, which one's irrational? So the difference between the two is going to give you the fraction, okay, with rational and irrational. So even though it's not written as a fraction when you have it in a section, can you write it as a fraction? Can I put -5 over 1 and have it be equivalent to a -5? So yes, I can write it as that. Okay, so next group of properties. I'll move up closure after you get the top two. So commutative property, associative property you've probably been exposed to previous years. Distributive property you've probably been exposed to. We always talk about distributiveness. Okay, but maybe some of these other ones here not used to. Okay, identity property. So commutative property, the same thing's on the left as what is on the right, but it's written in different order. Okay, they're still equal to each other and balance out, but they're written in different order. So you can change the order of what you're adding or multiplying. It doesn't have to be that. Okay, associative. Notice the left side and the right side are exactly the same. So associative will always be left side, right side are the same. It's just the way that they group them. Okay. So this group is different than that group, but they're still written in the same order. Okay, identity property means it's going to stay identical. Okay, when you add 0 to a number or subtract 0 to a number, okay, it's not going to change that number. It stays the same. Okay, identity, identical. And then distributive property, hopefully you've seen that. That's combining addition and subtraction, or multiplication and addition and subtraction. There should be a parentheses at the end of this A times C. There should be a parentheses there. So closure property, it holds true for addition and or multiplication, addition with any whole numbers. So the sum or the multiplication of any two whole numbers will be a whole number. So you're not getting negative numbers, you're going to get whole numbers. Okay, so substitution property, you actually had some on your review and your placement test, the very first ones where you plugged in the value for a number, okay? So that's just substitution is what that is. So you've been exposed to that. So substitution property of equality explains that one value can replace another value in an expression or equation, and the value will remain the same. So an example, and you guys will write examples like this. So if p is equal to 3, and then you give the equation that you're picking, okay, and p minus n equals -2, then I can replace the p in the equation with 3, so that I have 3 minus 2 equals a -2. Okay, so you'll write what you pick, what the equation is, and then what does the substitution look like. The transitive property, you don't have to write transitive property twice. This one's just an example of what it would look like with the equality, okay? And this is still transitive properties, you don't have to write it again. But that's just an example of what it would look like minus the equal sign with a greater than less than. So just write transitive property equality and have your two examples. Okay, so the thing on this one is now you have 3 different things that you're comparing, okay? So I'm comparing on this first one, A, B, and C. Okay, so if A is equal to B and B is equal to C, then if I take these 2 out, those B's out of there, then I also know that A is equal to C. Okay, and then here it compared the numbers 7, 8, and 10. Okay, and just rewrote it with an inequality versus an equal sign. So that's called transitive. Okay, remember in the future, if you ever miss a day that we're doing notes, where do you find a copy of the notes? On the calendar. So I'll have a recording, like I'm recording this class. All the YouTube link on there, so if you ever go back and hear it again and go back to your notes, because a lot of times you're writing and you're not really listening, okay? Some can multitask and write and listen at the same time, so. Okay, also those that are still writing, keep writing. These notes are great. Like, I'm just not standing up here wasting time. By you copying these down, you're getting points for them. When do you hand these in so that I can check them? Lesson quiz. So today we're going to do notes together. You're going to do the try it. It won't, first or third period didn't get done. So I'm assuming you probably won't either. Some did, but some had a few left. So we'll grade it tomorrow at the beginning of class. Go over any questions before you do the lesson quiz. So you'll do the lesson quiz, but you get to use your notes. So you're going to have the vocab and some samples to use on the lesson quiz, okay? And then you're going to hand that in, and that'll be part of your points for your lesson quiz. And that'll be how I know you took notes or not, okay? When we go to take the test at the very end, when we do sections 1 through 7, you're going to be allowed a note card. So then just, because we'll do a review before then, if there's things that you just can't remember, write it down on the note card, and you'll get to hand that in with your, you don't have to. It's just going to be an option. Otherwise, it's closed notes. Other than that note card. Okay. So keep that in mind. Okay, so on this page, you only need to write the top part. You do not need to draw this. I'm just going to talk about where this is coming from and what we did last year, but we're not doing geometry, so I'm just going to talk about that. So just write reflexive property and some examples. Okay, but leave that triangle thing out. I'm just going to talk about it when you're done writing. Okay, while you're writing, I'm going to do some talking. So reflexive property, to me, reflection, I just remember it when I start to memorize these. It just reminds me of a reflection. So when I'm looking in the mirror, it's still me. It's not something different. I'm not flipped around. Okay, it's still going to be the same. So the left side and the right side are exactly the same. Okay, now this is not the same as the associative and commutative. Associative and commutative, associative, they're in the same order, but you've got different groupings, so you've got parentheses. Okay, this doesn't have parentheses. Okay, so reflexive, what's on the left side is exactly the same on the right side. Okay, so this is where the drawing's coming from. So last year when we did this, remember how we kind of skipped over the proofs and I said we're not going to worry about that just because it wasn't on your state test. If you take college courses and you have to have some math major type stuff in there, you'll probably have a class that's just writing proofs. Okay, so this is where it would come in. I just want to explain it to you. Okay, so when we did, if I say that these two triangles are the same, they're the same triangle. We had a section where it was ASA, side angle side, angle side angle. Do you remember that? And we used the letters ASA, SSS. Okay. So this one with the tick marks, I would know that this side and this side were the same because of the tick marks. Okay. And then here I would know that this one and this one was the same. But that's only 2 things. I need to know a third thing. So if there's something that was shared in that drawing, which is what? The middle. The side shared, right? Well, since it's not labeled, this would be the reflexive property if we were writing proofs. Okay, so this is what the proof would look like. AB is congruent to CD because the tick marks AB and CD, they were marked, okay? Or AB. Oh my God. They actually have a marker on this picture. That's weird. Okay, they're saying that AB and CD were congruent to each other because of tick marks. The letters on here are wrong. And then AD is congruent to BC, okay, because of the tick marks. But AC is congruent to AC. There was nothing marked, okay? So we would just say we know it's because of the reflexive property, because it is the same line. It's me looking in the mirror. It's the same person, okay? So this would be where you would fill in your proofs. So when you know something, you write the property. When you know something, what property is that? Okay, and this one would be reflexive because the left side is equal to the right side. Okay. And then we call this side, side, side because it was just the sides that were labeled. Okay, almost done. Symmetric property of equality, different than reflexive. Symmetric. Keep writing. I'm just going to talk a little bit here. So symmetric property of equality is similar to reflexive. It's still equal what's on the left side and the right side, but it's not exactly the same. It's not identical, okay, like reflexive was. Okay, so the left side still equals the right side. So if A equals B, then you could flip it around and still say B equals A. So it's not the same letters or the same numbers, okay, but they're still the same is what they're saying, okay. So another example would be 1 plus 2 is equal to 3. Well, the same is true that 3 is equal to 1 plus 2. So you're taking the left side of whatever the first thing is and flipping it to the right side, okay? So where we did this in shapes, had nothing to do with numbers and shapes, is we had shapes and you had to draw the line of symmetry. So remember when we had a smiley face, you drew it right down the middle so that we can find that line of symmetry. So that the left would match up with the right, meaning it's the same thing, okay? So similar to reflexive, but symmetry is two different things, but they mean that they're equal to each other. Okay. I think this is our last one. Okay, inverse property of addition and inverse property of multiplication. Yeah. Okay, so with inverse property of addition, you're doing the opposite so that you can get to 0. Okay, so opposite of A would be a negative A, or opposite of a negative A would be a positive A, so that it gets me 0. The opposite of a positive 5 is a negative 5. Okay, the negative 3 would be a positive 3, so that it gets you to 0. So adding gets you to 0. Okay, but when we say the inverse of multiplication, it's flipping what you have upside down. So if it's a fraction, okay, you change the top number to the denominator, okay, and then vice versa. So like A, I could write that as A over 1. Okay, so the inverse of that is 1 over A. Okay, if I have 5, right, we could write as 5 over 1, so the inverse of that would be 1/5. So it should always come out to equal 1. So multiplication is 1, addition is going to be equal to 0. Okay, what's the inverse of it? So with adding and subtracting, it's positive, negative. With inverse, you're doing the reciprocal is another word that you've heard it. You're flipping. So we're looking at, and I just got to show whoever's absent today what they're going to. So we're looking at starting on number 23. Because I'm not going to keep it up on the board, I just want to show. So those that missed today and were absent, you're going to get on the calendar and open this up and follow along. I'm just going to be writing answers on the board. Okay, so looking at number 23, it says write an example of substitution property. Okay, so you have an example in the notes. I'm going to write something you think it's different than what's on yours. So when you write this, you're going to have an if, an and then a then. Okay, and then you come up with what you're going to write. Okay, So if, and I'm doing substitution, so you just pick a variable. So if, and x seems to be the common one that we mostly plug in. So if x is 2. Okay, so I have my if part. The and part is just writing whatever equation you want to write. Okay, and I have x plus y equals 4. So I have my if part, my and part, then is now using the substitution and replacing your x with the value that you choose. Okay? So mine would be 2 plus y equals 4. So I just wrote an example of it. Okay? And you can make up whatever one you want. Okay? Sometimes you'll be writing them, other times they'll have it, and they'll say which property it is. And you would say, oh, that's substitution, because they're telling you to plug that into that equation. Okay? So there's an example. Okay, so number 24. It says name all the sets of numbers of which a negative 7/9 is an element. So you're looking at the very first part that we wrote in our notes. Okay, where you had all those examples that you wrote off to the right-hand side. Okay, is it a natural number? No. Okay, would it be a whole number? No, because it's negative in a fraction. Okay, is it an integer? No. It's negative, but it's not a whole number. Okay, is it rational? Yes, because it's written as a ratio. It doesn't matter if it's positive or negative. So you can either write the word or just circle it or underline it. I think circling and underline probably is faster. Okay, well, if it's rational, it's not irrational, right? So we don't fill that part out. Is it a real number?
Yes.
Yes, all numbers are going to be the real numbers. Okay, so you have 2 of them that should have circled or underlined. Okay, the next one is write an example of transitive property. So transitive property, when you're looking at it, is you are comparing 3 different things. Okay? And I don't remember what letters were in ours. Was it A and B? Okay, I'm going to do different letters. So I'm going to say if x equals z, and w equals z, then what else could I say? X equals w. Okay, x equals w. So you're just taking the 2 z's out of that and what was left. Okay, that's your transitive. Okay, what is number 26 an example of? They wrote the example out. What is 26 an example of? Substitution. Because it's just like what we did on number 23. So you'd write substitution. Okay, now associative and commutative. Associative is written in the exact order on the left as the right. They just have grouping different. Commutative is what's on the left is same thing on the right but scrambled. Okay, so which one is 27? Commutative, because it's not in order. It goes A, B, C, and then the one on the right is B, A, C. So commutative. Okay, you're going to need calculators because you'll need it on your try it too. So if you have a calculator, get a calculator out. And you will only need it for these square root roots. That's the only one that you're going to need it for. Some of you have square roots memorized, others you need the calculator. Okay, so if you put the square root of 143 into your calculator, is it rational or irrational? Irrational, because the decimal goes off and it's not repeating, right? It doesn't go 1, 2, 3, 1, 2, 3, 1, 2, 3. So that one's going to be, yeah, just underline or circle. So on 28, it's irrational. Okay, now we have reflexive or the symmetry. Okay, the difference between the two. So 29, is it reflexive or the symmetric? Symmetric. Because remember the reflexive, the left side and the right side are exactly the same. It's you looking in the mirror. Okay, but symmetry, it's flipping it. Okay, the left side is flipped of the right side. They're still equal to each other, but they're different. Okay, so number 10, they want us to write an example of reflexive. So it doesn't matter, you pick any number, any letter, whatever you want. Whatever you write on the left, you write the exact same thing on the right. So I'm just going to make it easy for me, and I'm going to put 10 equals 10. That's an example of reflexive. It's exactly the same on the right as it is on the left. Okay, yes? 29 is symmetric. Okay, 31. Is 31 rational or irrational? Rational, because what does it wind up being? 18. So I could write 18 over 1. So it's rational. Okay, we've had one like this. What is 32? Which property is that? It's comparing three things. What? Transitive. Transitive. Okay, 33. Right. The reflexive. Yeah, it's the mirror. Yeah, the reflection. Reflexive. Exact same thing on the left as it is on the right, just like our 10 equals 10. Up. Yeah, we do. Symmetry is that, but it's split. So the two seem similar. Okay, so 34, now we're picking out all of the ones that are rational numbers. So I don't care if you circle or cross off the ones that aren't, just make it obvious. Okay, I did arrows for mine, but you can do whatever you want. So is 31 rational? Yes. Yes. Rad 11? No. No. So you can either cross it off or just underline 31. 2.79? Yes. Yeah, because we can make that as 279 over 100. 0. Yeah. We can make it into a fraction. We can make it as 0 over 1. As long as 0 is not under the line. Okay, negative 6.99 repeats itself. Remember what he said about repeating ones? Does that count as rational or irrational? Yeah, he started writing it. He says, well, we can write it as with a bar over. So that would make it as rational. What about 5/8? Yeah, it's a ratio. Okay, negative 6? Yes. So the only one that wasn't rational was rad 11. Okay, so we're back to commutative and associative, number 35. Associative is exactly the same on the left side as the right side, just the grouping's different. Commutative is not. So which one is this? Commutative. So associative and commutative, the only difference is associative, same on the left, same on the right, the order of the numbers, 1, 2, 3, 1, 2, 3. Okay. 36. Okay, it says write an example of the symmetric property. So this one, the left side is the same as the right side, but not literally. It just means the left side equals the right side. Okay. So I could go if 4 plus 5 equals 9, then what? 9. Right. So you just flip it. It still is the same. It's just not exactly the same. The left side equals the right side. So 9 equals 4 plus 5. Okay, 37. Comparing 3 instead of just 2. Transitive. Good. Okay, true or false? You have 50-50 on this. Okay, real numbers that cannot, the key word here is cannot, be expressed, indicated. What is a quotient? What does quotient mean? Division. So divided. So think of a fraction. Okay, top being divided by the bottom. Okay. So it says real numbers that cannot be expressed as indicated quotients of two integers are rational numbers. False. They have to be, right? So that'd be false. They're just using different words than ratio, comparing two numbers. Okay, 39. Name the irrational number in the set. Rad 5. Is there any others? No. Rad 5 is the only one. All the other ones you could represent as rational. Okay, number 40. Remember the order? So on the, yep, associative. So the left side is exactly the same order as the right side. It's just parentheses are in a different spot. So it's 5, 2, 3, 5, 2, 3. Commutative, you'll scramble the left side from the right side. Okay, 41. Associative again. It's ABC, ABC, they just grouped it differently. Okay, this one we have not had, number 42. The only kind of error, I don't know if it was meant to be or not, they left the word whole out of this sentence. So it says, what property is illustrated by the fact that 98 plus 62 is a number? It should probably be a whole number, would be the proper terminology. What one was the one that had to be a whole number? Closure. You add whole numbers, you're going to get a whole number. So that's closure. You don't see that one very often, or at least I have. Okay, 43. What is the one where you add 0, it stays exactly the same? Identity. It stays identical. It's not going to change because you're not adding or subtracting anything from it. Okay, 44. Associative. It's 15, 77, 24. 15, 77, 24. Okay, Brad 7 is an example of what? Irrational and real, because real is all numbers. Irrational and real, so 2 of them. Okay, and then the last one, true or false, irrational numbers are real numbers, which is what we just answered before. Okay, so that's what this one's going to be like. So you're going to try it now on your own, and hopefully without asking me, you're going to refer to this or your notes. We'll grade it at the beginning of class tomorrow and go over it. And then you get to use this and your notes on the lesson notes. Does that make sense? Okay, just so you get used to that. The routine. Okay. So once you get to try it and go work together, you can work together on it. If you get done early and want to hand it in, I had a couple of people that did. You don't have to, but your basket are over there. Make sure you hand it in to the class. Yeah. And I'll get the light. And technically this is supposed to be reviewed from algebra. I don't know whether or not you guys were exposed to this. So the first part of algebra is going to be reviewed. Algebra 2 is going to be algebra review.